Okay, so this video is going to be on Proton NMR. I'm not going to focus on the principle of how Proton NMR works, but I'm going to just try and work through how we can interpret a Proton NMR spectra. So the first thing you want to be focusing on is what are the different bits of information that a spectra will tell us. Now, if we're completely talking about an exam question, the marks come through using all the information that has been provided for you in an exam. A small number of marks will be available for the final product, but the lead up to that final product is where all the marks are. So you could get a 10 marker with 2 marks only allocated for the final product, and 8 marks will be for the working out. So if you got the final product, you will only get 2, and vice versa. If you did all the working out and didn't get the final product, you could possibly get 8. So the working out is by far more important than just the final product if we're thinking about maximizing the marks. Okay, there's firstly 4 bits of information that you need to be aware of when you look at the spectra. So the first one is the number of proton environments. So that tells us how many different proton environments there are, and that is just probably the easiest bit to decipher. You can look at the spectra and you'll see the number of peaks, and generally that tells you the number of proton environment. We'll look at it in a bit more detail on what that looks like. The second bit of information that you need to be thinking about is the integration pattern. So that tells you how many protons are in that particular environment. As in math integration, we mean the area under the graph, area under the curve, and that usually comes in a ratio. So what you need to do is you need to use that ratio to work out the smallest whole number ratio, and then you can use that to find out how many protons are in that particular environment. The third bit of information is the splitting pattern. So the splitting pattern is all about adjacent protons. Okay, so it's all to do with how many protons are adjacent to the proton in question. So that gives you the third, and the fourth one is the chemical shift. So that is usually used to work out the functional group. You use the data sheet for that. So those are your first 4 bits of information that you need to be looking out for and trying to use the spectra to work out as many things as you can from each of these 4 bits of information. Okay, so let's take this information now and we will use this information in an example here. Okay, so this is a typical spectra. Now, there's a lot of information here that we need to break down. So let's just look at the question. So it says the hydrogen NMR spectrum of C9H16O2 is shown. So that's obviously particularly important because that gives you your molecular formula. The compound has a large peak at 1705, so this is to do with infrared spectroscopy. So here that should give us a bit of information. You should be quite aware of this, as it tells you that there's a carbonyl. It does not react with sodium hydrogen carbonate, so that again, a bit of information. It tells you that it most definitely isn't an acid, so not a carboxylic acid, or Tolin's reagent. So it doesn't react with Tolin reagent, so that means it's not an aldehyde. So that leaves us with a couple of other functional groups that we could probably consider. So ketone is obviously one of them, and secondly probably an ester or something around that. So that's the first bit of information. Now we've got this spectra. It's proton environment. You can tell from the low chemical shifts. And the first thing you want to be looking at, like I said, is the number of proton environments. So we can see that there's 4 proton environments. You've got 1, 2, 3, 4. So that's 4 proton environments. Then we need to look at the integration pattern. So it gives you these numbers. So 1.2, 1.2, 5.4, and 1.8. So essentially what you want to do is you want to use the smallest of all of the numbers. So it's obviously 1.2. So if you divide this by 1.2, that gives you 1. Divide this by 1.2, that gives you also 1. 5.4 divided by 1.2 is 4.5. So that's 1.2 is 4.5. And then 1.8 divided by 1.2 is 1.8 divided by 1.2, that is 1.5. So we need the smallest whole number ratio. So as you would with empirical formulas, you need to multiply everything by 2. So essentially what you've got is you've got 2 hydrogens in this environment, you've got 2 hydrogens in this environment. We've got 9 hydrogens in this environment because it's 4.5 times 2. And then we've got 3 hydrogens in this environment because it's 1.5 times 2. So that's quite a useful starting point where you can see you've got 9 hydrogens in one environment, 3 hydrogens in one, 2 hydrogens in another, and 2 hydrogens on the other. Now, let's look at the third one, so the splitting pattern. Now, what you want to do here is look at basically the high resolution spectra, and it tells you what the splitting pattern is. So this is a singlet, so we will call that a singlet here. This is a quartet, so quartet. Now in an exam this should be a bit more clearer. This is a singlet, so we call that a singlet, and this is a triplet. Now identifying them as these splitting pattern usually equates to a mark, so that's obviously a useful thing to do. Now the last part is looking at the chemical shift. So this is where we need to start thinking about putting this whole thing together. Now the splitting pattern is relatively useful, probably not as useful as the other bits of information. If we look at these two, so this is about 1, this is about 3, and you use the data sheet, you will see that around 0.7 to 1.2 is the chemical shift for an RCH3. So that sort of tells us that it's these two which go into the RCH3 group. This one is around between 2 to 3, and again between 2.1 to 2.6. It's a functional group where you've got a carbonyl and a carbon and a proton. So it's this proton that they're talking about, and it's a quartet. So that's the other functional group. This one is a bit unusual. We can't quite work out what this might be at the moment, but we'll have a look at it in a minute. Right, now we need to start focusing on putting this substance together and putting some of the information and try and work out what it's actually saying. So I'm going to have to use a different sheet. So what you're looking here is you're looking to try and use information to work out some possible structures. Now, an easy point to start with this structure, with this spectra, is looking at this. Now, you've got 9 hydrogens in one proton environment, and it's a singlet. Now, that's a very common substance where you've got a methyl group or 3 methyl groups, all of them in the same environment. Now, because this is a singlet, so you can see this is a singlet, that means it can't be adjacent to any other protons. That's why it is a singlet, and there is no splitting of that peak. So this is a possible structure for this peak. So that's the first part. So you can say, okay, so we'll label this as A. So this is A. Now we then need to look at another possible structure. Now then what you want to look at is these two hydrogens. There's two hydrogens and three hydrogens. Now, you've done enough organic chemistry to recognize that if you've got something that's got three hydrogen, it's most likely to be a methyl group. And a two hydrogen is most likely to be CH2 group. Now, if you look at the splitting pattern, the three hydrogen is a triplet. Remember, the triplet means that it's adjacent to N-1, or it's an adjacent to two hydrogens. And then quartet means that it's adjacent to three hydrogens. So if you've got a CH3 and a CH2, they must be next to each other, because that's the reason why you'd get a triplet and a quartet. So your possible structure would be a CH3 and a CH2. Now again, if we think about it, this is the three hydrogens, so we'll call this B. So this is part B. And then these two hydrogens, we'll call this part C. This is part C. Now, the three hydrogens is adjacent to two hydrogens, so that's why this is a triplet. And then the two hydrogen is adjacent to three hydrogen, that's why this is a quartet. And that completely makes sense for the triplet and the quartet to be here. Now, if you then look at this chemical shift, so this chemical shift is around 2.1 to 2.6. So that tells us it's next to a carbonyl with the carbon and the hydrogen, and these two hydrogens will be the two hydrogens there. So we can then say that, well, there must be a carbon with an oxygen, and these two hydrogens are the ones that are giving you the chemical shift of 2.1 to 2.6. So we've just put those two together. Then you've got this random peak here, which is a bit further out from all the other chemical shifts, and it doesn't quite fit in. You know it's two hydrogens. You know it's going to be a singlet. Now, we've accounted for all the hydrogens here because you've got 9 hydrogens there. You've got 3 hydrogens there, so that's 9, 10, 11, 12, 13, 14, and these two will be 15, 16, and that gives us the 16 hydrogen that we need. So these two hydrogens can't be next to any other hydrogens, and they can't be, and they're both in the same carbon proton environment. So essentially what we're looking at is another carbon hydrogen, and then that's what gives us, but this carbon has to then be next to no other protons. We can't put another proton here. So if we look at the number of oxygens here, it probably needs another oxygen, and it's probably another carbonyl. And so we've got this side of the molecule, and then we've got that. Now essentially what we're looking to do is just putting them two together. And what you've got is, if we move this around and we say that's your 3 hydrogens there. So that's first part B, and that's the 2 hydrogen, which gives us the quartet due to these 3 protons. Then we've got the carbonyl, and that's due to the chemical shift at 2.1 to 2.6. Then we've got 2 hydrogens as a singlet. They can't be next to anything else, and that's due to, that gives you this peak. And then we've got our carbon with the 3 methyl groups attached to it. That gives us the 9 protons, and that would be essentially the final product. Now, your marks come in all of this analysis work. Mentioning that it must be, it can't be a carboxylic acid because it doesn't react with sodium hydrogen carbonate would equate to 1. Mentioning that Tollens reagent oxidizes aldehyde and not a ketone, and there's no reaction for that, so it can't be an aldehyde. Mentioning that the carbonyl peak on an infrared spectroscopy is at 1705. Those bits of information are all crucial to working out the structure. But the marks are in here. The structure can be slightly different. Sometimes you might get 2 marks for the correct one and 1 mark if you've got this methyl group, this CH2 group somewhere else. A number of students put it in here. The problem if you swap these around is that this will then have some splitting because of these 2 protons, and these 2 protons will have 3 on this side and 2 on that side, so there will be multiplets. So that's why it has to go in the middle between the 2 carbonyl. Right, so that concludes this question. Now, in the real exam, in an AQA exam paper, it's probably unlikely that you'll get something this substantial, because it would have to be worth at least 10 marks, and that obviously eats into a big chunk of the marks available for the paper. But there might be a smaller example compared to this. But essentially, these are all the skills that you need to be able to interpret the NMR spectroscopy.